Hi everyone. So I wanted to start this lesson by revisiting two variations on the second problem I did last time. This is the problem where we had the set point plus 10 degrees Fahrenheit, you might remember. So we needed an add block, and this was sort of the simple version of that problem. Let's remind ourselves how we did that. So in this problem, you have a temperature dial and we have a temperature sensor, and the thing is they're both on the same scale. So the dial bits and the sensor bits are exactly the same. And so if you go to my page of notes where I did all my calculations, you can see the strategy there. And let me switch over. So I thought it would be better to actually spend some time and make these notes without the tablet. So I've drawn it out for us here where the dial and the sensor, they have the same span and they have the same zero. So what makes this problem easy is they have the same number of bits per degree Fahrenheit, which I've highlighted in blue here. So if you remember what we did, the strategy was to take 10 degrees Fahrenheit, and we're just going to use an add block to add 10 degrees Fahrenheit. Of course, you're not adding the number 10, you're adding the bit equivalent of 10. So we had to, that was the main calculation here, where we take 10 degrees Fahrenheit times the 246, and this is what we're adding. So we did this in two steps. We had an add block where we added the 2462 to create this %r variable, the set point. And the key part here, the key strategy for analog variables is you're using comparators to turn these into discrete variables. Is the temperature greater than or equal to the set point, which is D1 plus 10 degrees Fahrenheit? And then you get this hot coil that you actually use in the ladder. If it's on, then your temperature is hot. If it's not on, then your temperature is not hot. So let's look at this first variation. I gave that to you in the Brightspace files, and it looks like this. The only thing that's changed, I highlighted, the only thing that's changed here is now the dial, which is the thermostat essentially, the user controlled dial, is on a different scale. It's starting at the same point, 70 degrees, so it's got the same zero, but now it ends at 135. How does that change the problem? Everything else is going to be the same except for the addition, something we have to add basically. So what is that? And that's what I really want you to think about. And I'm going to go to my notes. So let me click over. Okay, so the difference here now is that we've got two scales, but now they're different. So you've got the 70 to 135. You've got the 70 to 135 on the dial and 70 to 200. So before, these bits per degree Fahrenheit were different, and now, or before they were the same and now they're different. And so we have to fix that, because remember the last step of this in the comparator, when we are asking is the dial or is the temperature greater than the dial, those have to have the same number of bits per degree Fahrenheit. If they don't agree, then that's not going to work. So there's just a span adjust we have to do. The span adjust is pretty simple. The number is going to work out pretty simply, as you can see here. And I wrote it out as an equation, but the question is, if you take the dial bits, 492 bits per degree Fahrenheit, times what number, what multiplier gives you the 246? And I say the numbers work out easy because that multiplier is just 0.5. If you take the dial bits and multiply by a half, you get where we're supposed to be, like in agreement with the sensor bits. So you could either multiply by 0.5 or divide by 2. Our software doesn't let you do anything by one half, so you can't multiply by 1/2, you must divide by 2. So we have this intermediate step here. We have to take what's coming out of the dial, D1, and we've got to divide it by 2. And then we get a new adjusted signal from D1. And so I gave myself a new variable called D1 fixed, just so I can route it. I can route it to the appropriate place here. So all this variation involves is adding one extra block here, this divide block. So the first thing we're doing is we're taking the D1 bits and dividing by 2. And that'll give me what I'm calling D1 fixed, just a new variable, because now it's not D1 that I'm adding 10 degrees to, it's D1 fixed. And that's how I get my set point. And then the essential step, you're asking, is the temperature greater than or equal to that set point? All right, so let's look at the third variation. The third variation is what you can see here is, so this is 2016 Quiz 6 Variation C. I don't know why I call it Variation C. It's the second variation, second and last variation. But in this one, you can see both the span and the 0 for the dial are not matching that of the sensor. And again, the rest of everything else about the problem's the same, so I'm not going to go over it. I already recorded a screencast on that. But what do you do to make these bits in the dial agree with the temperature sensor bits? And so this is extremely common in instrumentation. Like when you're calibrating an industrial sensor, and they always work on a range like we've been talking about all semester, what you're doing is you have to set the span and you have to set the 0. So in this variation, we must do both. We must both adjust the span, and that's a multiply divide operation like we did previously, but then we're also going to have to make this 0.85 degrees agree with this 0.70, and that's going to be a plus minus operation. Here you can see which one it's going to be. It's definitely going to be a minus operation. We have to take 85 and we're going to subtract 15 degrees to get it to 70. Let's take a look at my calculations. So that's in my third layer here. Okay, so if we go to the top, you can see the changes I just talked about reflected in these graphics where you have two different scales, and I worked this out so it's the same scale change as before. We have, even though the actual scale is different, when you divide 32,000 by this range, you get 492 again. And so yeah, the first step is a span adjust. You must make these bits per degree Fahrenheit agree with these bits per degree Fahrenheit, like that arrow. So the first step is just the same as it was before, and I wrote out all the notes, but it's pretty easy to see. 492 times what number, what multiplier, is 246. Again, it's 1/2. So in the first step, it's the same as the other variation where we have to make a new D1, where we take the original D1 and divide by 2. But now we've got this 0 adjust, and this is also quite straightforward. For this 0 adjust, the math, what you're asking is 85 plus what offset equals 70. So of course the offset is 15. That's easy to see. You don't need an equation to see that, to recognize that the 0 adjust is minus 15. So we have to make a second adjustment, which is to subtract off 15 degrees. And of course, we're not subtracting the number 15. You have to do everything in bits. So that's what this calculation is. It's minus 15 times the number of bits per degree Fahrenheit. So our second adjustment is we have to take our adjusted D1 and subtract 3692. So we're going to have a subtract block. Now what you can see is I gave myself yet another variable to store my second adjustment. Let's take a look at the analog blocks. I didn't quite have enough room to fit it all in one line. So here's where we're starting. We're taking the D1 from the original dial, dividing by 2 to get this adjusted or fixed D1. And here's the new part where I'm just taking that and I'm subtracting the 15 degrees. So this is 15 degrees in bits. And so I gave myself another variable for that. You don't have to do that. Like, you could, if you wanted to, you could do that where you're just taking D1 fixed, subtracting off 3692, and then storing that new number in D1 fixed. So you're essentially replacing the contents of D1 fixed with this new number and writing over it. I chose to not do that just for clarity, but if I undo all this stuff, it's not like you have to do this. You don't need an extra variable, but it's just a little more clear that way. And so the last two steps are the same, where we're taking our adjusted dial that's been adjusted now for span and 0, adding the bit equivalent of 10 degrees, so adding the 10 degrees, and then the comparator is the temperature greater than the set point, greater than or equal to the set point. So that's how that works. I really wanted to show that to you. All right, so let's go back to our homework problems. There's 4 homework problems. Just as a reminder, you're doing them. I'm covering them in the screencast. This is your main studying tool. We're on number 3. Let's take a look. So number 3 has a lot going on. There's 3 analog variables. There's level, there's temperature, and there's also a user-controlled dial for a temperature set point. And we're looking at that, and you can see that the scale for the sensor, temperature sensor, is the same as the scale for the dial. So there's none of the scaling that I was covering previously, and so that makes your life a little bit easier. The level sensor goes from 2 to 10 meters, and the temperatures, those scales go from 50 to 120. And so we've got a tank, heat, stir. If you look at the description, you've got to fill the tank, you've got to heat and stir, and you're heating until you get to that set point that's indicated on the dial. Gonna keep heating and stirring for an additional 3 seconds, so you know you're gonna need a timer, and drain the tank to 5 meters. So I'm seeing 3 set points there, and repeat for a total. Repeat step 1 twice for a total of 3. So you know you're going to need a counter. So there's a lot of stuff you can put in right away before you even start. So I'm going to ask you to attempt the problem if you haven't already, and I will go through the solution. Okay, so let's look at the calculations first. So I will pull up my calculations. So here's number 3. And so I've tried to stay consistent with this system that I've developed. So here we are with number 3. And the set dial and the temperature sensor, they're on the same scale. So you can see that they're matching. When you divide the 32,000 by the scale, you get 457.14 bits per degree Fahrenheit. It's the same. So it's very simple. The hot temperature is just, all you need is that comparator, is the temperature greater than the set point. and these are both coming from built-in variables. So this is coming from the sensor, so that would be a percent AI, and this is coming from, the set is coming from, that's coming from the dial, so that would also be a percent AI analog inputs. And so you just have this hot discrete variable. So I'm going to go to my scratcher. Here it is. So I gave myself, actually I gave you all a place for hot. So here's hot. You're using a greater than. I'm activating that with a master. And so you get a hot signal when the temperature is greater than the set point. Okay, let's look at the other variables here. Those are going to be the levels. So with the levels, there's no dial. There's just hardwired set points. So the difference is with the temperature, there's a user-controlled set point. Here, these are built in. We got the 6 meter and the 5 meter set points. So first of all, you figure out the bits per meter, which I did over here, 4,000 bits per meter, nice clean number, and then you're just calculating your 2 set points. And remember, the key here is you're not starting at 0, so you can't just take 6 and 5 times their scaling factor. You must subtract from the 2. So we just get 2 set points, the 6 meters and the 5 meters in bits. And so this is pretty straightforward too. We just are going to need a greater than and a less than. These are actually greater than or equal to, less than or equal to. So that gives us a TF signal, a TE signal. The only thing you have to just be aware of is these are working differently than natural level sensors, because the TE sensor, that's going to give you a true when the tank is empty. It's going to give you a true when the level is less than the equivalent of 5 meters. So you just have to keep that in mind when you're doing this ladder. So let's go back to the ladder, and that's what these are. I have a greater than and a less than. So I gave myself a tank full sensor and a tank empty sensor, and I've got my bits built in here. Maybe I'll increase the size of my eraser here. Okay. That's usually what I like doing first. Perhaps you do too. The next thing I like to do is take care of any other timers or counters. So in this problem, I know I have a, the timer is gonna be timing for 3 seconds. You can see I've made an adjustment here. So 3 seconds, so I need time for 3 seconds. So, sorry, I called it 5 seconds here. That's because this used to be a 5-second problem. And so I got that, and I need a counter that's going to count to 3 drained tanks. So I'm not revealing the logic yet, because that's not how I generally do it. I just want to get all my architecture in there. And now this just becomes a discrete problem. So let's just go ahead. I'll reveal the free mark here, the master. And so I know this program's going to cut when I get to 3. That is really the only point of this counter. When we get to 3 drains, then we cut. So we've seen this a lot. For that reason, we have a normally closed 3 in there. So that cuts the whole program. Okay, so the first thing this thing has to do is fill. And so the fill conditions, I believe, are the first things I have here. So here's fill conditions and the fill action. I probably should have called this v-in conditions, but I called it fill conditions. And so the fill conditions, fill is the first thing that happens, and you can't really assume that this tank is starting empty. So what would be the fill conditions? Well, the fill condition is basically just that you do not have a full tank. So the only thing I have in here is normally closed, besides the master, normally closed TF. So if this tank is not full, then you're filling. And any other limitations for tank filling are going to be handled with fail-safes. So, for example, when the tank is draining, this is also true. When the tank is draining, the tank is not full, so this would be lit up, but we're not actually going to be activating the fill when it's draining through fail-safes. So the V in action rung, I've got my fill conditions and a bunch of fail-safes. Okay, so my maybe my next step here is heat and stir. So I've got heat and stir conditions, and then I've got heat and stir. Notice I gave stir a little motor signal just for good form. So the heat and stir conditions, I'm thinking about two things. The heat and stir has to start when I have a full tank, so TF. And I'm using generic contacts because this is not a sensor, this is a memory coil that I made through my comparator. That's the whole method here. And then heat and stir is going to cut at the end of the time. I'm looking at number 3, heat and stir for an additional 3 seconds. So when the time expires here at 3, when that lights up, that's going to cut this. So I'm thinking normally closed. Whenever you want a high signal to cut something, you're talking normally closed. And so on my action rung, same pattern. I've got my conditions, and I'm preventing draining or filling through fail-safes. And the last part of this program are the drain conditions, which are always like the trickiest part on a tank, but hopefully you're getting used to them. So here's my V out conditions and my V out. So V out conditions, that's step number 4. That's the last step here. You have to have a full tank and your time has to be expired. And then we'll cut that when the tank is empty. So full tank, TF, normally open. You also have to wait until the timer expires. So definitely a normally open. And again, sorry, this is 5 seconds. That should definitely be a different label. That should be 3 seconds. I think 1 year I changed this, and well, that's what we're stuck with. And so this is going to drain until you get a empty signal. So here's what I was talking about before. How are you going to cut this V out when the tank goes empty? You have to keep in mind that TE, that's going to go high when you have an empty signal. So you want this active TE to cut this, definitely a normally closed. And you must latch. You must latch anything that's going to drop out as soon as V out starts happening. So that would be both the high level signal and also the timer will cut out. And here's the action rung. So I've got my V in failsafe here. So for that reason, that's why I can get away with this very minimalist fill condition of just not tank full. Because I also have that fail-safed, the V in is fail-safed here. So that's going to work. And my last steps here are my timer. So you want your timer, the timer starts at, the timer starts after you've gotten to a hot temperature. So I'm looking at number 2 there, heat and stir. Actually, it's step number 3. You heat and stir, and then at step number 3, once you've reached the temperature set point, you heat and stir for 3 seconds. So the timer starts when you're hot. And last part of this, before the prize, last part of this is, what are we counting? Well, you want to count 3 total drained tanks, and we've talked about this a bunch. The best thing to do, you don't want to count V out or anything like that. If you count the number of times the tank goes full, and you count to 4, then you're always going to have three total drained tanks. So it's going to fill and drain for 1, fill for number 2 and drain, fill for number 3 and drain. It's going to fill that 4th time. And then the program will click off. So it's going to end with a full tank. But that's totally fine. And I'm going to reset this with a normally closed master. a normally closed master, meaning that when the program deactivates, then you reset your counter. All right, so did you get that one? We will move on to the very last part of this, problem number 4. This is a variation on the combination tank and tub problem we did before, but I added a twist here. Now there is a controller, a control dial for heat time. What does that mean? So let's take a look and definitely attempt this one on your own. A conveyor moves these 3-gallon tubs into place, and the tank, there's 1 gallon represented in between the full and the empty set points at 80 centimeters and 15 centimeters, so that tank level is working on an analog input. And you can see the scaling here, 10 centimeters to 100 centimeters. And so when you look at the event sequence, the conveyor starts when you push on, and so the tub moves into position and the conveyor stops, and then a bunch of things happen. You fill to 80 centimeters, and then you drain to 15, and you're going to repeat that for 3 total tanks. So that's a lot like what we just did. Now, after that's completed, so this is a little different. D, with 3 gallons in the tub, we turn on the heater, and the duration of that heater is controlled by this user-controlled dial. And the scaling on the dial, you can see that right there. It's 0 to 32 seconds. So that's interesting. So that's going to be going to a timer. So that's something new to think about. That's why this problem is in here. How can you get an analog input to interface with a timer? A 1/10 of a second timer. We'll stick with that since that's what we've been using. Okay, so yeah, the tub moves into position. We get 3 gallons drained, which is working on an analog level sensor. And after that, we activate this heater for a certain duration of time. So I'm going to keep doing what I have been doing and start with my calculations. So let's turn this off and go to my calculations. So I have everything on one page here. The level is the easier part, where we've got 100 centimeters. This should be 10 to 100 centimeters. I'll fix that in the notes. And so we've got our calculation that we keep doing. You're always dividing 32,000 bits by your scale in your physical parameter there. And when we do that, we get 355.56 bits per meter. So this is very straightforward. This is just like the last one, where you get a certain number of bits per whatever, in this case, meters. And there's 2 set points to calculate, an 80 centimeter set point and a 15 centimeter set point. And we get a certain number of bits, and it's very straightforward. We've got a tank full signal, TF, and a tank empty signal, ones with a greater than or equal to, and ones with a less than or equal to. So I like to just, since I've done that part, I like to just put that in my ladder. So I'm going to go to my ladder and reveal that part. So we never did the prize for the other one. What is that prize? I'm sorry, you guys. What is the prize? What is the prize? No, Photoshop does not want you to get a prize, but I really do. It's money. Okay. I don't think there's a prize on this one, unfortunately. So I've got my TE and I've got my TF, so let me reveal those. And I've just calculated set points in bits. So level is greater than 24,889 and 1778. And those are just hardwired onto masters. Okay. The other part, though, is that time dial. I'm going to have to deal with that. So let's deal with that now while I have my calculations out. Okay, so here's the thing. We're starting out the same, where you've got heat time, that's the variable, and that's scaling from 0 to 32 seconds. So we do our division problem, and we get 1,000 bits per second. 1,000 bits per second right there. But of course, the timers we're not using 1 second timers. If we were, then you would want to use 1,000. And on a quiz, if you really want to, you can use the 1 second timer. But I'm going to show you how to do this with a 1/10 of a second timer. So if it's 1,000 bits per second, then hopefully it makes sense that it's 100 bits per 1/10 of a second. But we want to figure out the time target here. So what I've worked out is that time target, that's the number you put in front of your timer. For most of the problems we've been doing, that's just been a constant. But here, this is different. This is not a constant. This is coming from a dial. So the question is, based on this dial, how do we scale the time target? Because you wouldn't just want to put heat time in here. That wouldn't make sense, right? Because like 1 second would be 1,000. So if you put heat time in there for 1 second, you'd have 1,000. That's not 1 second. If you put 1,000 right there, then of course that's going to be 100 seconds. That's not going to work. So there's a lot of different ways to figure this out. Perhaps what I just said kind of gives you an idea of how to do this, but I guess the most formal way is what I did here. The question is, how many 1/10 of a seconds for the timer? So that heat time, all I did was I just kind of calculated what the heat time is. It's just the number of 1/10 of a second times 100 bits for every 1/10 of a second. So if you want to back solve that, if you want to know not what the bits are, because remember, this is in bits. Sorry, I was just adjusting my brush there, don't mind me. So you don't want to put the bits in there, you want to put the number of 1/10 of a second. So I'm just rearranging this equation. So what you have to do when you look at that rearranged equation is recognize you got to divide. Like if, for example, if you have 1 second here, then heat time for 1 second, based on this, nice clean numbers, you get 1,000 bits. If you wanted this timer to time for 1 second, you wouldn't put the 1,000 bits in there. You'd put in 10. So you can see that to get from bits to the 10 you would want down here, you're clearly dividing by 100. So all of that means that we need to have an intermediate step for the timer, and that is a divide step. So we're going to take the heat time, which is in bits, because all our analog variables that are coming from in or out are in bits, and we have to divide that by 100, and that's going to give us a time target. That time target is in 1/10 of a second. So this divide block is just taking our heat time, which of course is in bits, and dividing by 100, and that's going to get us this variable, this time target, which is in 1/10 of a second. That's what needs to go into the timer. So these are separate lines. So let's go to the ladder. Okay, so that's what the divide block is for. You're going to take the heat time and divide by 100 because of the calculation I just showed you. And that gives you your actual time target. And again, what I mean by time target is that time target is the time target in 1/10 of a second, because that's what we're using in our timer. So I have the timer here, heat off. I called the timer coil heat off because that's what the timer's supposed to do. And time target is the input there. Okay, now let's think about the rest of this program. So got my start stop master, And is there anything else that's cutting start stop master? If you look at the program description, if you look at that program description, there's not. This is just going to restart. There's a world in which this program has another counter to just repeat this cycle, this tub cycle, a certain number of times, but that's not what's going on here. So the master rung does not have anything else cutting it. Okay, so the first thing that happens are my motor conditions and my motor action. And we've seen this from the beginning. The motor condition is just a normally closed position sensor. And I think we all understand why that's working. That's just going to keep the motor running until the tub is in place. And as soon as the tub's in place, that opens up. And we have that bypass that I guess I'll reveal at the end, even though you guys probably know what it is. And I've got my action rungs where I have some fail-safes. I have an optional fail-safe. Fail-safes are often optional, but I guess I found it important to explain that here. Okay, the next thing that happens when the tub is in position is we've got this fill drain action. So this is sort of like a program within a program. We're just filling to tank full, draining a total of 3 times. So this is pretty much exactly the program we have been sort of repeating on and off, where I made one condition, the VN conditions. So the VN conditions are, you probably want to start with tub position. So the tub has to be in position. I see how I said that was optional. So the reason I said that was optional is because if you think about it, like the tub wouldn't technically have to be in position under the valve to start the filling. Like it's maybe okay if the tank is filling while the tub's not in position, because that's not dangerous. Of course, you would never want to empty when the tub is not in position. I think I feel better if this is here. Although if you were looking for efficiency, then maybe, yeah, you want the tank to fill whenever it can. And so we're just saying the tub is not full. And that's the VN condition. And so here's VN. And so all these optional clouds, they represent the possibility that I just described, that if you want the tank to fill when the tub is not even in position, then you would get rid of these. But if you want everything to happen just as soon as the tub is in place, then you keep them. And so the V out is just the opposite of that. So you definitely need a tub position. So I've sort of, I think for space, I've just put my condition and action rung in one. But for V out, the tub is in position. So that has to be true. That's not optional because, of course, the tub's there and you can't drain without a tub there. And we've seen this before where you have a full tank and this is going to cut when the tank goes empty, so normally closed there, and you must latch with itself. And we've got some fail safes here. Okay, so that gets us through part C here. So we've repeated for a total of 3 tanks. And so now that part is done. And so we should probably program the counter, because the count is an essential part of that step. So give yourself a counter and call this 3. And when 3 goes hot, that's going to initiate the next step. Now, if we go and we look at the problem statement, you can see that I included this little Easter egg. I lost it. Where's the Easter egg? The Easter egg's right here. You can assume the tank starts empty. So if you can assume the tank starts empty and you've got more options. So see if this makes sense to you. If you can assume that the tank starts empty, then you can count the number of empty tanks, because you know that when this tub goes into position, you've got an empty tank. So if you can assume the tank starts empty, then you can count the number of empty tanks. And of course, then you'd definitely be counting to 4, because as soon as this thing clicks on, you're already going to get a 1 count. And if you want 3 total drains, then you got to do it 3 more times for a total of 4. And the other thing about this is, when does the counter reset? Well, unlike a lot of the programs we're doing, this does not reset when the program turns off. The whole point of the counter is to count a new 3 drains for every new cycle. So you've got some options here. I said M1, so anytime the motor turns on, then you can reset that counter so you can get back to 3 gallons. I also made a note you can use motor conditions. Of course, they're going to be on at the same time. And that'll work just fine. So that gets us through step C. And now we're ready for the heater. So the 3 gallons in the tub turns on the heater. So that's basically my last rung here. Sorry, I never unscratched or scratched this off. Okay, so my last rung here is the heater. And so the heater turns, what are the heater conditions? Again, I was bad and I did not give myself separate condition and action rungs, but I've got a master here. So clearly the heater has to turn on when you count to 3. And also your tub is in position, definitely. And then the last part of this is the heater is going to cut. The whole point is the heater cuts when your time target activates. So I've got to heat off. So the heater's activated when your tub's in position, you got 3 drains, and it's going to continue until heat goes off. So the last part of this is what goes in front of the timer. Well, I've also got this reset. So what goes in the timer? What activates the timer? When does the timer start? The timer starts after you've completed 3 drains. So I've got a 3 there. So as soon as I got 3 drains, the timer starts and the heater starts. So the timer activates, or sorry, the 3 counter activates 2 things. It activates the timer and it activates the heater. And when the timer expires, heat off, then that cuts the heater. And then when that's done, when all of that is done, so we've finished step E. It's time for step F. We restart the motor, and that's the bypass that I have strategically avoided here. So the bypass happens when your time's done. Heat off. And that's it. Wow. So you guys have come a long way. I hope this all makes sense. If you want to contact me for office hours, which could be a conference, it could be a phone call, let's do that. We're going to have our quiz the next time we are scheduled to have class, which is the Monday after spring break. I hope everything's going well. Sending you lots of love from San Francisco. And I'll see you guys next time. Bye.